Alright. Good afternoon, ladies and gentlemen. I hope you guys had a wonderful lunch. My name is Alejandro, Celauro, this is Andrés, Rueda, and this is Carlio, Porsenna. And we're going to be presenting today our project on overhead crane automation. So, we decided to go with a local company called AR, and they had a problem in their electroplating department. Their problem was that if a landing gear came into the department too late in the afternoon, they wouldn't be able to start work on it, refurbishing it until the day after. If it was a time-sensitive part, they would have had to pay workers overtime throughout the night to get the part done on time. For their electroplating department, the reason why they couldn't simply leave the part submerged unsupervised is because when the electroplating process is going on, chromium or nickel is being added to the part. So when excess chromium or nickel is added to the part, it later has to be milled off. And for anyone who's worked with chromium, they know that it's a very tough material, and it's really time consuming to mill it off, which can take hours depending on how many layers it's added. The motivation that we had was working with a real world problem and working with a real company rather than making our own project out of it. We wanted to utilize our engineering design principles in order to work for the real world side of things. So the solution that we came up with was to create an automated overhead crane for them, using their existing crane, so we would just retrofit them.
And the system had to have an easy to use interface. It also had to be affordable and also serviceable. Some background, interestingly, compound cranes were utilized as early as the ancient Greeks. They utilized 6 pulleys to create a 1-to-6 mechanical advantage, which allowed them to lift payloads as high as 6 tons. Later on during the Roman times, they created more advances in the crane technology, which allowed them to lift blocks of around 25 to 77 tons. They were used in conjunction with a lifting tower, which had several levels, and were utilized several cranes to create lateral motion and also lift parts as high as 38.5 feet. In terms of project objectives, we wanted to create an automated system that allowed users to provide time duration and also the location that the crane had to go. This would all be controlled by a pre-written program on the computer. In terms of global learning, we had to be mindful of where these parts will be produced, and also who would actually be able to, who would be using the products, in terms of like a local business here or somewhere abroad in Europe, maybe Asia, and possibly Africa.
So we decided to go about this project in making a kit. That way it's usable to not just the AR company that we're doing the project for, but also commercially available. Now this kit, thinking about other companies, would have to be separated into 2 phases. Phase 1 was making sure that the trolley had both horizontal and vertical capabilities, as to there are a lot of trolleys out there that just have the vertical capabilities and you just simply push the part around. After that, phase 2 is actually implementing the autonomous system into the crane. For the phase 1, we had 2 designs. One of them was the rack and pinion design. For this design, we were going to weld a rack onto the H-beam, and then replace 2 of the wheels with gears, making it the rack and pinion. The great thing about this is that it's a no-slip design, and it's very accurate in terms of positioning. But the drawbacks of this is that once you actually weld the rack onto the structure, the H-beam, it can create structural compromises and things like that. for the second design in phase one, we decided to go with a much simpler design, which was adding gears to the back of the wheels, as seen over here. So you would have 2 gears in the back of 2 wheels, and then you would have a third wheel on top, which would connect the 2 gears and move them, and that one would be where the motor is going to be at. The great thing about this is that it's real simple. You don't need major modifications or structural modifications to the HP. Now, for the first design that we had in phase 2 was for the analog system, which we were going to use analog sensors as well as an analog controller. For the controller, as you can see, we made 2 knobs, one for the timer that the part's going to be submerged, and the other one is going to be for the depth. That's going to measure how low the part's going to be submerged. We also made buttons for the bath number that the part's going to be in. This will all be made into a compact design that's going to be adapted to the current controller that they have. The advantages of this is that analog it's always consistent, it's reliable, and it's all a centralized unit. The drawbacks of this was that they all consist of cables, and running cables throughout the whole system and a moving system may create a hazardous environment. The second design was a completely wireless design, and for the controller we simply added a stop button which would transfer the controls from the wireless system to back to the manual system, and then vice versa with the other button. The great thing about this is that you would have a wireless interface on the wall, and then also a wireless sensor on the crane. This would give you minimum interference. It would give you great accuracy, and you wouldn't have any excessive amount of working parts.
We created this interface on Visual Basic, and it allows the user to actually input time in the first box, and in the second box it'll actually give you the end time, so you can figure out whether or not how long you have to pay the workers. And we also added features where you can actually add and subtract time, or maybe multiply and divide based on your specific needs, or in order to lengthen or shorten the time. And we also added bath locations at the bottom, which allows you to decide which solution you want to use. And as a redundant feature, the program cannot start without the bath location being selected.
So for our timeline, we superimposed a separate one onto it. Our original timeline was the plan, which is highlighted, and then our railroad tracks are for the actual timeline that we had. The reason why they don't match is because we went into the project thinking that we have a set budget that the company gave us, and we also assumed that the product was going to be approved in-house. Unfortunately for us, when we did go with our presentation, because of corporate bureaucracies, they gave us an estimated amount of time of 3 to 6 months for a decision to come back from corporate, which we're still waiting on. For the final design, we did choose the simple design of the two. We went with the geared wheel trolley.
All right. So our final design consists of primarily an electric motor, 3 gears, and a counterweight system. Now here we have the fully depicted system, how it would look like. Keep in mind the electric motor, the counterweight system uses the same frame as the electric motor. Now, in order to figure it out, our design approach towards it is we first looked at what's out there in the market. Harrison, they already have a similar half-ton trolley that has 2 settings of speed between 40 feet per minute and 80 feet per minute. So in order to do that, next we need to figure out what's the rotational speed of the wheel, how fast it needs to be rotating. After doing a little bit of math, we find that it's 65 RPM or 130 depending on the speed. Next we need to find the force. Something that we kept in mind, that was in our minds, is that if we put too much torque into the wheels, it's going to slip, and that's going to later on cause problems for this next phase when we're trying to have accurate control and precise positioning of the trolley. So in order to do that, we figured out first the weight on each wheel. We assumed that the load of half a ton or 1,000 pounds, which is going to be evenly distributed along the 4 wheels. So we have 250 pounds per wheel pushing down. The friction coefficient is going to be between 0.5 and 0.8 because it's iron and steel on steel. So we end up with a max force of 125 or 200, depending on which coefficient factor we use. And then the actual torque, we end up with either 220 or 252. Now, that we already have the rotational speed along with the torque, we can actually figure out how much power it's going to be required to move an individual wheel. That's what the table depicts right now. So, we have to multiply those numbers by 2. We end up using a 1/4 horsepower per wheel of power. Since it's 2 of them, half a horsepower motor. Now that we already have figured out the motor and the rotational speed, we can go into the gear train and start figuring out how we're going to design it. We decided to go for 3 identical gears in order to keep things simple for manufacture. They be about 3 inches wide and 36 tooth. Max speed, as stated earlier, 40 feet per minute. With a bending stress per teeth between, depending on how the teeth are made, how the gears are made, it could be anywhere from 15,000 to around 16,000 pounds PSI. And then because of that, we decided to go with carburized and hardened steel grade 1 instead of cast iron. Cast iron would be just break halfway through. And it has around a safety factor of around 3.4. Now that we already have the gear train, we can move on to the support that will hold the motor. The motor weighs itself about 26 pounds. However, since we're going for adaptability, this is not only for this one specific company, our product has multiple potential. We decided to go for it to have a carrying capacity of 40 pounds. We assume that it's going to be the worst case scenario, that people are going to have a little bit of difficulty installing the motor, that they might put the force too much at the very edge. So we assume that all the in our simulations and our calculations, we assume that the entire load is being carried just on the edge, just to maximize like worst case scenario. Under those circumstances, we find that the maximum stress is 7,600 psi, pounds per square inch, with a safety factor of 3.4. The frame itself weighs about 6 pounds, so it's quite manageable of weight. In addition, it has 2 points of contact to prevent it to prevent the moment of inertia from just simply tipping. And the 2 connection points would be downwards, the main crossbar, along with a 1/4 inch bolt that be attached between the already existing frame and the plate. It's important to note that the bolt itself has a capacity of 3,500 psi, so it's more than capable to hold the entire weight of the system should the lower section fail. Fabrication. Now, the gear train would be custom made. We were thinking about just simply buying originally we were thinking of just simply buying the gears individually and then kind of welding it, but then when we upon closer examination of the equipment that we have, we realized that it just wouldn't be really feasible. We would, it's impractical. We would not only would we modify harmfully the wheel design itself, but we would also damage the gears so it wouldn't properly mesh. So we would just simply decide to go for a solid piece that will be milled into shape. As for the frame support, we recommend that it be made out of single sheet of hot rolled steel plate, and it just simply be cut and welded into shape. Now, the manufacturability. It's really important to note that this design is very simple to execute. It doesn't require any high-tech technology. It can be easily outsourced to China, Latin America, Africa. All right, and yeah, and it allows for commercially viable products. All of our components can be just simply more or less bought off the shelf.
In terms of designing health considerations, we have to make sure that the design did not utilize any toxic or hazardous material, and also that the implementation of the design will not compromise the structural integrity of the support system for the overhead crane. In terms of maintenance, we designed the system so that it would coincide with the regular maintenance of the original manual crane, and that any major any major situation that will arise from a failure of the gear would also be spotted on early during one of these maintenances and not just create a workplace accident. The environmental impact that we had to consider was the replacement of the components, mainly like the gears. We had to consider that in terms of how often the gears will be replaced and also where the disposal and stuff like that will be done.
For the economic analysis, we figured for the initial overtime pay is, for every worker is about $22 an hour. You would need 2 workers and 1 manager. For the manager, it would be $35 an hour for overtime pay. And they would stay for approximately 4 hours every night. This would occur about twice a week, and this would come out to about $632 for the whole week, coming out to around $31,600 for the whole year, assuming that they do this twice a week, every week. Now, the total cost for the whole system cost around $8,600, but according to with what they're actually paying for overtime, they would get a return period of about 92 days, which is really impressive for any company.
In terms of risk, we have to make sure that the design did not compromise the structural weight bearing of the overhead crane. And we also have to make sure that failure in the crane, in the components of the design would not impact the overall use of the crane. The standards we utilized were the OSHA's the Occupational Safety and Health Administration's regulations, because they are mostly applied to businesses. AAR is primarily a business company and also he's subject to these guidelines and regulations. In terms of contemporary issues, the main one that glaring one that we can notice is the reduction of overtime pay for employees. In terms of like a global impact, this design can be implemented in almost any region. There's no ethical restrictions that will impede the use of this design or the production of its individual components. In terms of evaluation, we were successful in creating a design that can actually be produced in any part of the world, and also it has a low teaching level, which makes it easier to understand and utilize. In terms of commercialization, we're actually creating a kit that can actually be sold on a customer by customer basis and also customized based on the components in the workplace. In terms of future work, we're going to add sway control simply for safety issues, because when cranes are in motion, they sway a lot and can actually create workplace accidents and also provide a clear and present danger. And in conclusion, we believe that that automation can be accessible and also safe at the same time. In terms of acknowledgments, we'd like to thank Dr. Tosunoglu for being our mentor and advisor. We'd also like to thank Dr. Ziccarelli for allowing us to use this crane utility model and create the trolley. Thank you.
Any questions? Yes.
You're addressing issues and concerns that the company has with time and the concern of how is this going to help them in production to mitigate the concerns of high chromic or chrome deposits on the part and so forth. How did you come across, or what kind of analysis were you given in concerns that time? Did you guys do any time studies, or was some time studies given to you as to how much time do they lose with the current crane system that they have?
Of course. So when we came across, as they were explaining the actual issue that they had, they explained to us that the main issue with chromium is that for them, even 1/1000th of an inch, it takes them about an hour to mill. And just the operating costs of a manufacturing facility in Florida are $80 an hour. So just $80 an hour just for 1/1000th of an inch. And depending on the length of time, this is depending on the part itself, the wear and tear, remember, this is refurbishing. So sometimes some parts need a bit more of thicker coating than others. It can very easily get wild. We're looking even if just simply like a couple hours, $160 to $300, like easily.
So in this case, this particular solution is to lift up the part at the proper time?
That's the main original setup, is to help with the lights out operations. Just simply, once the worker already has set up the electroplating process, because that's something that we actually, as we're researching, we found out that we cannot fully automate it, at least not with the size of our team. It's just not feasible for us to undertake a senior design project. Perhaps if we had greater interdisciplinary collaboration, we might. But as of right now, we just focus on, all right, let's assist them in at least just stopping the electroplating process.
Yeah.
So to add to that, what the process was meant to do, it's supposed to, one, make sure that the part is in there for a specific amount of time. Once the part is actually done, it would shut off all the power to the electricity. For the electroplating, it would lift up the part and it would move it to a safe unloading zone.
And lastly, I saw that you did mention it with regards to the sway and the inertia. These are parts that are weighing almost a ton. I know for a fact because I work in the landing gear MRO. So what kind of contraptions or systems are you looking forward to controlling this MOI or swaying load of 6 or 7 feet long, 2,000 pounds worth of chunk of steel that you have to move from a tank that's about 12 feet deep all the way up to a safe zone?
Well, this is the part of phase 2. This is the part of due to time constraints and how originally we were going to be working with a fully motorized electric trolley. So we had to kind of backpedal a bit, and this is why it's a bit, not quite a set. But ideally, the original idea